Okay, the next talk is still going to be about skilling. It's entitled the Spring Rigs for Skilling. It's a work from Toothman and Neff from UC Davis. And Nicholas is going to do the presentation.
Thank you for that introduction, and thanks for warming up the crowd with some skinning info. Hopefully I'll flesh some of that out. That's the last skinning joke we'll make. So this was under the program under a different name, but we updated it. So if you search for it on ACM, use this title. So if you're not familiar with it, skinning is just a technique for posing meshes using a comparatively low amount of geometry, control handles of some kind. For characters, we use skeletons because they're intuitive and artists can pose them quite easily. So we want poses to look natural, we want shape change to look smooth, and we want to avoid certain kinds of artifacts. So if you haven't seen it before, this is the main formula for linear blend skinning. We're taking a weighted average transform of bones and applying that to a vertex in a bind position to get a skin position. So LBS and DQS both do this. These require skin weights, as we have already learned, but this is very fast, both to code and to execute, and it's frame independent. So if you need to batch render this, you can spread it out to a bunch of machines and get all of your frames rendered separately. So here's a quick look at some of the artifacts that we see. On the top is LBS with this candy wrapper twist. We get a volume collapse given these two bones. If this was twisted 180 degrees, we'd see a solution for one vertex being up here and another down here. So the average between those ends up in the middle and will lose volume. Dual quaternions don't suffer from this, but they have a very densely packed rotation in the center. So both of these things are something that we want to try and address. It's not just twists that have issues. These are some swing rotations. So we see some similar volume loss on the linear blend version. And for dual quaternions, we don't have that volume loss, but we do get a little bit of spherical bulge. And the rotation distribution around this bend is a little spread out. So those are some things that we want to try and fix. So we can do a few things to try and fix these kinds of artifacts. First, we can see if just changing the rig itself is sufficient. This means going in and editing our skin weights. There are a lot of really great methods for automatic skin weight computation, but usually the artist has to go in and do some work to refine things. And we also do things like insert support bones that don't do anything but remove influence from bones that would otherwise cause that kind of collapse. So these have become pretty common techniques for addressing certain artifacts. And the other approach is, of course, changing our skinning algorithm. So in this case, there's all sorts of great work out here. One that we leverage quite heavily off of is stretchable and twistable bones, where they take the skinning transformation and decompose the steps into swing and twist rotations, isotropic scale, and translation. You can also try to find an optimal center of rotation for vertices that are clustered by skin weight similarity to avoid that kind of collapse. And I'm especially partial to the implicit surface approach, where you partition the mesh into primary skin weight segments, form implicit surfaces, and then you can model all sorts of things like contact and get these secondary deformations like bulge. So our goals are to keep the convenience of skeletal deformation, but we want a little bit more control over the final shape, and we want to keep things fast and interactive, and ultimately we'd really like to keep some compatibility with the existing rigs that are out there. So our first approach at this was attachment-based character deformation, where we make this explicit connection between our mesh surface up here and the skeleton underneath. So each vertex has this attachment point, and the vector that runs between those, we just call it scale vector. So our observation was that if we can minimize the differences between adjacent scale vectors in the mesh, we can close these gaps and get some smooth deformations. And you may not be able to see it as well, but the larger this bend becomes, the more this deformation gets a point on it. So to fix that kind of pointed artifact, we have a length adjustment step that's in the poster abstract for this, if you're interested. But this approach was quite clumsy. It takes a good amount of decomposition, and it wasn't very flexible for complex meshes. So let's start with just a quick look at what the artifacts tend to look like. So we get some twist and swing artifacts with LBS, as well as bone length changes. And ABCD handles these issues quite well. And for really simple meshes, it's easy to see what kind of binding process is involved. Looks like it's a little choppy on the video. But with the meshes you're seeing here, you can already tell that the process for attachment to the skeleton isn't that difficult. When you start dealing with more realistic character meshes, areas like the pelvis and the armpits, where our schemes weren't really as applicable. But this kind of setup allowed us to play with all sorts of parameters to have more fine-tuned control around the joints. And that scale vector representation allowed us to do a little bit of surface editing on top of skeletal posing. So we have this bodybuilder pose with a little bit of labor breathing on the side, and the effect's fairly subtle, but it's something that can be keyframed and synchronized with your skeletal animation as well. So the attachment binding process, we took a naive approach initially, where we just wanted to see what the results would be if we projected vertices onto the closest bone in the mesh. But of course, for certain regions, if we were to take the scaled vector lengths and globally scale them down, we'll start to see these stretching artifacts. And we really want to avoid this kind of attachment scheme. So something on the right here is more what we're after, where we have this smoother change in the scale vector angles as we go down the bone, so that when we shrink it, we don't have this same kind of issue. And that was set up by manually tuning these partitioning planes at each bone, and then taking a signed distance test between the two nearest planes for every vertex, and then figuring out their position on the bone by using those distances as a weight. It was a huge pain to try and tune, and it wasn't much better than working with skin weights. So we took a different approach where we started with a direct projection onto the skeleton and then applied iterations of Laplacian smoothing to close those gaps. So we can iterate as many times as we need, but not many are really necessary. This one was got with about 6 iterations. So with the projective skinning, they inflate the skeleton, and with this one, we're kind of blasting it down onto the skeleton. So this attachment binding process is really just about making an explicit connection between the surface and the skeleton. This is something we've seen a bit before. So if the mesh has no skeleton at all, we can perform this contraction operation to try and estimate one. The stretchable twistable bones computation relies on these endpoint weights in order to support things like changes in bone length, and ABCD uses pretty much the same idea of the endpoint weights from this paper. And then of course the projective skin work also is concerned with this connection between the surface and the skeleton. So the results that we saw in the simple uniform style meshes were pretty nice. On the top we have LBS for comparison, but down here if you look at the back swing of this leg, it's not too bad, but when you look at the front swing, there's this kind of caved in region that just wasn't really working for us. So we wanted to move away from this really explicit style of skinning the advantage of our previous method was that it was direct. We could compute it in one pass, but the disadvantages were pretty apparent. So there were too many edge cases in our shaders. We implemented this in the programmable pipeline for skinning, which uses vertex shaders to change the positions or to compute the skin positions. But there were a lot of edge cases to make that work right, and it was difficult to generalize this for more character-like meshes. So we wanted to keep the same idea, minimizing differences between adjacent vertices, but make it more automated and make our jobs easier. So I turned to springs. And this isn't a brand new idea. The anatomically based modeling work in the past uses springs to bring vertices together, but in the context of having elastic membranes representing things like muscle and another tissue underneath the skin. The main difference that we see here is with our springs, we're not just dealing with connections between adjacent vertices on the edge lengths, but also dealing with the rotation or the angle between adjacent scale vectors. So the figure from our paper kind of outlines the main contributing spring forces. We have a torsional spring that tries to bring a vertex and rotate it closer to its neighbors based off of the distances there, and a linear spring that just tries to do the same thing. But we also need a bit of a restorative force to bring the scale vector back towards its bind angle with the bone it's attached to. And then to control the profile of a bend, we also have these forces that determine how much the length of these scale vectors should change as well. So we have 4 kinds of spring forces. That means we have 4 kinds of spring coefficients to handle. But these are all Hookean springs. So we use the same scheme from anatomically based modeling to figure out our default coefficients. We have a bias for vertices who make a right angle with their scale vector. And then we just leave the length coefficients for 1. So here's a quick look at a mesh skin with LBS. And our forces, just our attachment and our length, or our attachment and our surface forces. But left unconstrained, they can start to skew the whole mesh. So some regions are collapsing closer and closer to the bone surface. So the bone torque force restores that, but if it's too strong, you can just drop the coefficients a little bit. So the springs have worked out really nice, but you might wonder what could go wrong with springs, and if you haven't worked with them before, you might see stuff like this quite often. So how we handle convergence and look for thresholds is an important problem. We have a fixed iteration count, and we also look at the maximum position changes on each iteration. So we compare the position differences to the maximum bounding box dimension size, and whichever happens first helps us stop. So we do this all in compute shaders, observing that the forces should be equivalent between a vertex I and j, just with a sign flip, so we can pre-compute the displacements for edges first, and then run the compute shader to get a net force based off of the neighbors that it has. This means we need 2 buffers so that we can iterate and go frame to frame. And since we have potentially nonlinear deformations, we also have to recompute normals so that things are aligned correctly. But we get quite good run times. These are all in milliseconds, and for comparison, LBS implemented with a compute shader takes less than 0.01 milliseconds, so we're quite higher in all of our cases, but still something that's sufficient for real time. So we have LBS with the twist, and then DQS, and then our method down here. And for a swing rotation, again we have LBS, DQS, and we compare it with rigid scaling. And there's quite uniform results no matter which initial method you use to deform the mesh. So we have a few side-by-sides that we can show and then wrap things up. So on the left we have LBS, and on the right we just have our spring forces. and it handles twist and length change quite well. And you'll notice some differences, especially in the size. And you might wonder, if you're working with springs and recomputing this for every frame, do you have to deal with popping? There are a few cases where you'll see some popping regions on the mesh. We've also implemented this as a frame-dependent version where instead of running 50 iterations, we're using the last frame solution to increase the performance. And that usually eliminates the popping too. So we've seen the immediate results, and here are some of the solves over time, and colorization is just the magnitude of the forces on each vertex. So with the rigid skinning deformation artifact, we can see there it is. We can see the restorative behavior of the springs, and even with LBS as our initial find, we can still smooth out some of those results too. And what's really interesting is we didn't quite expect this, but we started to see some secondary behaviors that the springs gave us. So with the shoulder bend, we got a little more skin deformation than we expected to see. So we got the integrated solver. The results can be either configured to be independent or frame dependent. The convergence is somewhat tunable, and we get fairly smooth deformations with real-time performance, but we need to work on our frame-to-frame stability, and with that, a little bit of tweaking to our parameters. And ideally, we'd like to move to a solver that's kind of always on, so that we can, throw things at our meshes and watch them bounce off. And then look at attempts to bring in more author-driven surface deformations. Thank you.
Thank you for the presentation. Do we have questions? So, you talk a little bit about the divergence problem that is with springs, but which kind of integration, numerical integration, is it like explicit area that you're coding on the machine?
We did. Thanks. We tried explicit and semi-implicit, and ultimately we just ended up doing so we compute the net force on each vertex per frame, and then we find our next position just by taking that net force and multiplying it by a time step, and then applying that to the either the rigid scanning solution or the whatever method we use to scan first. So it's somewhat like position-based dynamics, where we don't have to worry as much about velocity or acceleration.
I have a question. I didn't really get how you're estimating those thickness parameters. Are they open parameters for the user?
For the coefficients?
Yes.
So these are also, we have global parameters for each of these too, so whatever these are computed as initially, the user can then fine-tune and weigh them so we can have more or less spring force for any of these factors.
So the user has to tune some global parameters?
Yeah, the initial values do a fairly good job, but if you want to change that behavior to suit your needs, you do have to go in and adjust those a bit.
And have you thought about not doing this in a time integrated method, but just solve the static problem, optimize for the lowest potential energy, quasi-static?
We looked at just looking at the potential energy stored in the springs and trying to find a minimum for that too, but this gives us kind of a foundation to hit those problems next.
Okay.
All right, thanks again.